Okay, so for RK4, the error also goes up because we have a fixed delta x up to somewhere around lambda equal 10. So because of that, as we increase lambda, if you do not change your delta x, the error goes up, which means in the log scale, you see this, the red line actually goes up to somewhere around, lambda equals 1, which is around here. Okay. And then after that, we start decreasing on delta x, so that's why the error goes down again. However, for an Adam-Moulton method or trapezoidal method, we do not change lambda, we do not change delta x, and we still do see the same thing. So after, somewhere around lambda equal 1, all of these methods are almost having the same accuracy. So in that case, RK4, which is fourth order method, is not so much different than let's say first order method like forward Euler. So they almost, have same accuracy, and that's because, before we change the delta x, then the stability is an important issue, and that's because of the stability, the error goes up for the red curve and blue curve, but then after that, because we use a smaller delta x, then the error goes back down. Okay, so this is showing that for explicit methods, we really have to change delta x as we change lambda. However, for implicit methods, like trapezoidal method or backward Euler, we don't really have to change delta x. We can still have the same delta x as lambda is changing. Okay, now, so this analysis indicated that when stiffness goes up, right, for explicit methods, we really have to make the delta x smaller, and that actually increases the computational cost if the lambda or the domain length is really large. Like in the robber problem, if we want to look at really large time period, or we want to understand the concentration of species in the long run, then our delta x, or say delta t, cannot be small, because if it's small, then we have to really cycle through many iterations to basically resolve the solution or find a solution for the whole domain length. Now, at the same time, if you increase the delta x, we see that for explicit methods, then the inaccuracy actually goes up, or the accuracy becomes worse, and that actually sacrifices the accuracy we want to get for the problem. Okay, so now we run into this stiffness problem, or stiffness issue for certain problems. Okay, so here is the example we look at. It's not the robber problem, but it's something similar to that. That means we have a differential equation, right, with let's say this form. Okay, and our goal is basically to solve the problem using one of the techniques that we learned so far. Okay, so we have three y's in here, y1, y2, y3, and the equations look like this. We have three equations, three boundary conditions. You can think of these as concentrations. Again, the concentration of A, B, and C at point 0 are these, and we see that if you look carefully, you see that these constants, which can be interpreted as the reaction rates, are vastly different. So we have reaction rate of about 10 minus 6 somewhere, and then we have reaction rate of about 1. So the coefficients are almost 1, except this guy, which is 10 to the minus 6. So there's about 6 orders of magnitude difference in the reaction rates. So the way we go about solving this is, well, if you want to really simulate this with our toy problem of dy dx equal lambda y, basically we have to linearize it. That means we have to linearize this nonlinear set of equations. And to linearize it, first we have to define the f, which is the right-hand side of differential equations. So we have dy dt, dy2 dt, dy3 dt equals these three. And then to linearize it, we get the derivatives of these equations with respect to the three unknowns, or the so-called Jacobian. So we form the Jacobian, whose first row is df1 dy1, df1 dy2, and df1 dy3. So here's f1, this is f2, this is f3. And by doing so, we get a matrix like that. Okay. So now we can linearize our differential equation like so. We say d vector y dt, okay, is equal to the Jacobian times the difference in the y's. The difference in the y is going to be y1 minus y1 at point 0, y2 at minus y2 at 0, and y3 minus y3 at 0. Okay, plus the y values at point 0. This is pretty much like Taylor series for vector functions. Okay, so this is the function at point 0. This is the derivative, the first derivative times the variation in the function, and so forth. So we do not actually have the second order term, we just drop it because this is about just linearization. We only keep the linear term. Okay? Now with this matrix of Jacobian, we're going to go ahead and find the eigenvalues. Okay? Now we're going to define the stiffness for the problem which is more than one equation, right? Again, this problem is not similar to the toy problem, but we are trying to make it look like the toy problem. So the toy problem was a linear problem, dy dx equal lambda y, and because of that, we linearize our nonlinear problem. We get the lambdas to be the eigenvalues of this matrix, and then we're going to define the stiffness this time as the ratio of the maximum real part of the lambda divided by minimum of the real part of the lambda. So if we have a matrix of 3 by 3, then we have 3 lambdas. We have to find the real part of them. We find the maximum value of the absolute value, actually, of the real value divided by the minimum of the absolute value of the real value of the eigenvalues. Okay, so the larger this ratio, the larger the stiffness. And the larger the stiffness, the more problem we have solving it. Okay, and if you do so for this problem, you see that it's about 10 to the 4, and this is really large. In the realm of stiff method or stiff problems, 10 to the 4 is a rather large number, which means the problem is already stiff. So there are a few options in MATLAB that we can go ahead and use. For this part of the course, actually, we do not really write any code for stiff problems, because these are really more involved and these are delicate problems and need a very robust algorithm. So one option is we use ODE 1.5 in MATLAB. So this is basically based on RK methods, but it uses actually two types of RK methods. First order and fifth order. So it's going to use first order when it reaches the time period where the function decays really slowly. So the first order would be enough. I mean, we use like some sort of not really accurate method, large time scale. So that is referred to ODE1, which means it uses RK1 with large delta x for part of the problem where decay is not fast. However, looking at the part of the reaction where things are happening really quickly and reaction is really fast, this ODE 1.5 is using RK5 with much smaller delta t or delta x. Okay, so this ODE 1.5 means somewhere along the domain we can use we're going to use RK1, and somewhere along the domain we're going to use RK5. RK5 is much more accurate than RK1, and we use it when the rate of the reaction is really fast and the rate of the reaction is really slow. Then we're going to use the less accurate method, which is RK1. Okay. How to switch between RK1 and 5? This is what MATLAB does adaptively. So it actually finds where the solution is changing fast or slow, and based on that it changes the order of the RK method from 1 to 5 or vice versa. Okay, so the logic behind it is actually boiled down into this method called gear method. This is a combination of multiple versions of RK method. We don't cover it in class. I left this as a final project. If someone is interested, can work on gear method, which is like adaptive RK methods for stiff problems. All we use for now in class is just the built-in functions, but we don't really get to the details of this and be able to change the order of method. But if you really want to do it, you have to get into the details of gear method, which is which can be chosen or selected as a final project. Okay, so let me skip through this, the details of it, the proof of it, and 1 or 2 examples on the gear method. So we're going to skip all this and directly go down to MATLAB built-in functions for stiff ODEs. Okay, so that is on page, at the end of page 149. So there are multiple functions that we can use in MATLAB to solve ODE problems. Okay, so I list them here. We have ODE45, which is not really for stiff methods, where if the stiffness is not too large, then it's okay to use ODE45, which is a combination of RK4 and RK5. MATLAB is using RK5. Well, basically RK4, and whenever it becomes inaccurate, it's going to switch to RK5, which is a bit more accurate method than RK4. Okay, so the problem type is for usually not stiff problems, or stiffness is not too large. Accuracy, I think it's medium. We have other options, ODE23, which is based on RK2 and RK3. This is also for non-stiff problems. And the accuracy is low, because the order of accuracy, you see, that is less than 4.5. We have ODE113. This is again for non-stiff problems, and the accuracy can change from 1 to 3, which means from low to high. Usually for stiff problems, we're going to use ODE15S, which means the combination of RK1 and RK5 for stiff problems, and the accuracy is about low to medium. We also have ODE23S. For stiff methods as well, because the order of accuracy is less than 1 and 5. Well, actually 3 is less than 5, you can think of this way. The accuracy of that is actually low. And I have some quick comments of where these methods can be used. For instance, ODE15S, you use that one if the ODE45 is a slow, or there's a mass matrix. I mean, we didn't talk about mass matrix for now, so we can skip this part, but usually if ODE45 doesn't work, we're going to switch to 15S for stiff problems. Okay. There are other comments here. For instance, for ODE45, we're going to use this actually most of the time, and it should be the first solver that you're going to try. Okay, for ODE23, so this is going to be a crude approximation for the solution of a differential equation. Or if you really have like moderate stiff problems, we can use ODE23. So you can take a look at other comments and see where it is applicable to the problem. Okay, so there are a few things in, let's say, in using these functions, especially about the tags or labels or arguments that we have to use. So stay tuned for the next video on how we use ODE45 and ODE15S in MATLAB. Specifically what labels and arguments we have to use here in terms of the tolerance, thresholds, and so forth. Okay, so thank you so much for watching. Stay tuned for the next video on MATLAB built-in functions for solving ODEs.